Okay, now let us solve partial differential equations of homogeneous type. Homogeneous type means partial differential equations involving right hand side zero function, and here in this case they are involving only one independent variable, either x or y. Suppose there is an example: solve the PDE dou square z by dou y square plus 3 into dou z by dou y plus 2z is equal to 0. So this is called homogeneous partial differential equation, because right hand side is there is no function, only 0 is there, and it is involving only one independent variable y. So that is why this is known as PDE of homogeneous type. So in homogeneous type, what do we do here is we will convert this kind of PDE into ordinary differential equation of order 2. So how it can be converted? We transfer or we change dou z by dou y is equal to dz by dy. If it is dou z by dou x is present, it will be changed as dz by dx. And in second order term, dou square z by dou y square is changed as d square z by dy square. That becomes ordinary differential equation. So that is here, it is written here. So our PDE, given PDE was this one, and it is changed as or converted as d square z by dy square plus 3 dz by dy plus 2z is equal to 0. So this becomes ordinary differential equation. And you know that how to solve second order or higher order ODEs, ordinary differential equation, when right hand side is 0. We will find only complementary function by using auxiliary equation or by solving auxiliary equation of this equation. So that is, in this equation again change operator d2 or dy by d by dy2 operator d square y dy square to operator d square. Then this equation becomes, equation number 2 becomes d square z plus 3dz plus 2z is equal to 0. And that is the dependent variable here, you can take as common variable, and then this is called auxiliary equation d square plus 3d plus 2. When this is equated to 0, it is called auxiliary equation. And we will solve this auxiliary equation for the roots of this equation like this. Split 3d to d plus 2d, and you can solve like this. Factorization: d plus 1 into d plus 2 is equal to 0. Equate each term to 0, you will get one value or one root of this equation will be d is equal to minus 1, d is equal to minus 2. These are real roots. Then the solution is written as, solution of this equation is written as z equals c1 e to the power minus y plus c2 e to the power minus 2y. So here c1 and c2 will be again replaced in the form of function of x, because y is the independent variable and x is also independent variable, but x is not present in the equation. In this equation x is not present, so x will be taken as or assumed as constant. Therefore this c1 is replaced by f1x. f1x is constant function. c2 is replaced by f2x. f2x is a constant function. Then the final solution will be z equals f1x into e to the power minus y plus f2x into e to the power minus 2y. So this becomes the solution of homogeneous partial differential equation. So another example: solve dou square z by dou x square plus z is equal to 0, and given conditions are when x is equal to 0, z is equal to e to the power y, and dou z by dou x is equal to 1. So first let us change this PDE of homogeneous type to ODE, ordinary differential equation, by writing the dou square z by dou x square as d square z by dx square. So it is written here d square z by dx square plus z is equal to 0. This is the conversion of PDE into ODE, and then we will solve this. So use operator d here or d square d square is equal to d square by dx square. In this place we are writing d square. So it is becoming d square z plus z is equal to 0. Then solving auxiliary equation, d square plus 1 is equal to 0. So that gives roots as d is equal to plus or minus root of minus 1, or it is plus or minus I. It is a complex root or imaginary root. So you know how to write the complementary function when root is a complex number or imaginary number. So in that case we write solution as z is equal to c1 cos 1x plus c2 sin 1x, that is c1 cos x plus c2 sin x. Now change c1 and c2 by corresponding constant function. Here constant function is f1y and f2y. So then when you change c1 by f1y and c2 by f2y, it becomes z equals f1y cos x plus f2y sin x. So now let us find what are these constant function values. So for that purpose we use given conditions. So using condition, that is when x is equal to 0, z is equal to e to the power y. So put z is equal to e to the power y here and x is equal to 0 in cos x and sin x. Then we will find that it is f1y cos 0 is 1 plus f2y sin 0 is 0. So becomes f1y value is e to the power y. So you got f1y value as e power y. Next, to find another value called f2y value, what is the condition given in the data? In the data it is given that dou z by dou x is equal to 1 or in transformation it is dz by dx is equal to 1 when x is equal to 0. So we need dz by dx. Therefore for that purpose you differentiate this one. Z is equal to e power y cos x plus f2y sin x will be differentiated with respect to x. Then dz by dx is equal to e power y written as it is, same constant, cos x derivatives minus sin x plus f2y as it is, sin x derivatives cos x. Now use the condition dz by dx is equal to 1 and x is equal to 0. So left hand side it is 1, sin 0 is 0, cos 0 is 1. So f2y remains, f2y value will be 1. Substitute f2y value in equation 3, it becomes z is equal to e power y cos x plus sin x. This is the required solution of given homogeneous PDE. And one more example, we will follow same method. It is also second order PDE. Dou square z by dou y square is equal to z. Given conditions are when y is 0, z is equal to e power x and dou z by dou y is equal to e power minus x. So again we follow same method. We will convert that into ODE and the form of d square z by dy square is equal to z, or d square z minus z is equal to 0, d square minus 1 into z is equal to 0. Auxiliary equation is d square minus 1 is equal to 0. Solve this, you will get two real roots, that is plus 1 minus 1. Then we write solution z equals c1 e to the power plus y plus c2 to the power minus y, or change c1 and c2 by corresponding functions or constant functions f1x and f2. So now let us find what is f1 and f2 using given condition. So given condition is y is equal to 0, z is equal to e power x. So substitute z is equal to e power x and y 0 here, you will get this expression. And then to apply second condition, differentiate equation 2 with respect to y. Dou z by dou y is equal to f1x e power y minus f2x e power minus y. So using this condition we will obtain that e power minus x on left hand side and f1x into e to the power 0 is 1 minus f2x e power 0 is 1. So we will get expression for this one as f1x minus f2x, that is equal to e power minus. Let us solve equation 3 and equation 4. So then we will get f2 value as cos hyperbolic x, f2x value as cos sin hyperbolic x. Substitute in the solution. Solution is z equals cos hyperbolic x e power y plus sin hyperbolic x e power minus y. This is the required. So in next example, solve dou square z by dou x square plus 3 dou z by dou x minus 4z is equal to 0. Given that when x is equal to 0, z is 1 and dou z by dou x is equal to y. So this is involving, you can observe this is involving only one independent variable x, and right hand side it is 0. So easily we can transfer this to ODE by choosing dou by dou x is equal to d by dx, dou square by dou x square is equal to d square by dx square. So then it becomes d square z by dx square plus 3 dz by dx minus 4z is equal to 0. And now to solve this equation, use operator d, that is using d is equal to d by dx is equal to d square by dx square is equal to operator d square. Then this equation becomes d square z plus 3dz minus 4z is equal to 0. Choose the dependent variable z as common variable, and this is d square plus 3d minus 4 into z is equal to 0. So now we have to solve this one using complementary function method. So then for that purpose the auxiliary equation is d square plus 3d minus 4 is equal to 0. So let us factorize this. D minus 1 into d plus 4 is equal to 0. Then solving each term, d is equal to 1, d is equal to minus 4. So we write the solution or the complementary function z equals c1 e power 1x plus c2 e to the power minus 4x. Now changing c1 and c2 to constant function, that is in place of c1 we write f1y, in place of c2 we write f2y. And then let us apply the condition when z is equal to 0, z is equal to 1 when x is equal to 0. So z is equal to 1 and x is equal to 0, you will get this kind of expression 1 equals f1y plus f2y. This is one equation, call it as equation number 3. Now differentiate equation number 2 with respect to x partially. Differentiating 2 with respect to x partially, dou z by dou x is equal to f1y as it is, e power x differentiation same e power x, plus f2y as it is, e power minus 4x differentiation is minus 4 into e to the power minus 4x. Now apply the condition, that is dou z by dou x is equal to y when x is equal to 0. So this is dou z by dou x, on left hand side it is y, and x is 0 here, it becomes f1y minus 4f2y. So we got again one more expression called as equation number 4. Solving equation 3 and equation 4. So then subtract 4 in 3. 3 minus 4 gives 1 minus y is equal to 5 times f2y, or f2y is equal to 1 minus y by 5. Similarly, equation 3 multiplied by 4, add equation 4 to that. Then we obtain 4 plus y is equal to 5 times f1y. So f1y is 4 plus y by 5. So substitute this f1y value and f2y value. Final solution is z is equal to 4 plus y by 5 into e power x plus 1 minus y by 5 into e to the power minus 4x. This is the required solution. So in this discussion we have understood how to solve a homogeneous partial differential equation by converting into ordinary differential equations. So next we have another kind of partial differential equation called Lagrange's linear partial differential equation. So Lagrange's linear partial differential equation is also a kind of partial differential equation which is read as, or which is in the form of, it is product of some function of xyz called f of xyz into dou z by dou x plus product of function of xyz into dou z by dou y is equal to another function of xyz. So we have three types of functions here involving variables xyz, f of xyz, g of xyz, and right hand side also function of xyz. And now we use some notations for these partial derivatives. Dou z by dou x is written as small p, dou z by dou y is taken as small q, and first function f function is taken as capital P, g function is taken as capital Q, right hand side function is denoted by capital R. So this Lagrange's linear partial differential equation in short form is written as P into P plus Q into Q is equal to R. This is the representation of Lagrange's linear partial differential equation, where P stands for dou z by dou x, small q stands for dou z by dou y. Now, how to solve this Lagrange's linear equation? So here we follow some steps. These steps are involving auxiliary equations and then grouping method and also selecting multipliers. So one by one let us observe. For this kind of Lagrange's linear equation called P into P plus Q into Q is equal to R, we write one auxiliary equation known as or given by dx by capital P is equal to dy by capital Q is equal to dz by dr. These are some ratios. So these ratios are together called as auxiliary equations. Now these ratios will be grouped in two types of groups, that is dx by P is equal to dy by Q and dy by Q is equal to dz by dr. How we can select these? So by observation we can observe that these are easily integrable. These are easily integrable. In such a way we have to group. And then another method is choosing multipliers or using multipliers. Say some constant, maybe lmn or numbers 1, 2, 3 or any other function of independent variables we can select. Say here we have selected lmn as the constant terms. So then here there are three ratios. By choosing lmn, another three terms or three constants, we can write fourth ratio as these three ratios is equal to ldx plus mdy plus ndz divided by L into capital P plus m into capital Q plus n into R. And then we can solve by grouping or by choosing multipliers. We can solve, we will get two solutions. By solving this one, dx by P is equal to dy by Q, we will get solution as u of xyz is equal to a, and by solving dy by Q is equal to dz by dr, we get another solution v of xyz is equal to b. Then these two solutions will be combined in the form of f of, use arbitrary function f here, f of u comma v is equal to 0 or f of a comma b is equal to 0. So this makes the general solution of Lagrange's linear partial differential equation. So here important observation is you have to write auxiliary equations or ratios and then grouping method, or you can choose multipliers and then find the solution. You can also combine. If for one solution one group will be selected, for another solution we can choose lmn or any other variable terms as the multipliers and write fourth ratio and then solve it. You will get two solutions called u function is equal to a and v function is equal to b. Combine them in this form called f of uv is equal to 0. So we will obtain the solution. So this is the method of solving Lagrange's linear partial differential equation. Okay. So one example let us observe here. Solve the PDE P tan x plus Q tan y is equal to tan z. So this is by observation easily you can find that this is a Lagrange's linear equation because it is P into capital P plus Q into capital Q is equal to R. So this is Lagrange's linear partial differential equation. So this is Lagrange's linear partial differential equation, where small p stands for dou z by dou x, small q stands for dou z by dou y, and this is in the form of p into capital P plus q into capital Q is equal to R, and where capital P is tan x, capital Q is tan y, capital R is right hand side function R is tan z. So now let us write three ratios called auxiliary equation, that is dx by capital P is equal to dy by capital Q is equal to dz by capital R. That is dx by tan x is equal to dy by tan y is equal to dz by tan z. Now we have to think of finding solutions in two functions called u and v. For that purpose, let us consider any two ratios, that is called grouping method. Now grouping the two ratios, first two ratios as dx by tan x is equal to dy by tan y. Another group is dy by tan y is equal to dz by tan z. Then first group, let us integrate both sides. Integral of 1 by tan x dx is equal to integral of 1 by tan y. That is 1 by tan is cot x and 1 by tan y is cot y. Integrate them. Log sin x is equal to log sin y plus log of a constant. Only c1 we can write. Let us avoid c1. We write log c1. So then shift log sin y to left hand side. It becomes log sin x minus log sin y. Nothing but log sin x by sin y is equal to log c1. Cancel log sin x by sin y is equal to c1. This is one function we got. Similarly, this group will be solved by integrating. We will obtain another solution. Sin y by sin z is equal to c2. So we got two solutions. We will call this as u function. We call this as v function. Combine them. F of c1 comma c2 is equal to 0, or f of sin x by sin y comma sin y by sin z is equal to 0. So this makes the general solution of Lagrange's linear equation. Okay, next example. Solve x into y minus z into p plus y into z minus x into q is equal to z into x minus y. We can observe small p, small q are for dou z by dou x and dou z by dou y, and this will be chosen as capital P and this will be chosen as capital Q. Right hand side function will be chosen as R. Therefore, it becomes capital P into P plus capital Q into Q is equal to R. That is Lagrange's linear equation. Now let us solve this Lagrange's linear equation. Write three equations or three ratios called auxiliary equations. Then dx by x into y minus z is equal to dy by y into z minus x is equal to dz by z into x minus y. Now here grouping is not possible. Why? Because if I choose these two ratios, first two ratios, dx, and this is involving, denominator is involving x, y, z, right hand side dy in denominator involving x, y, z. So we can't integrate. Z cannot be eliminated. So we can't integrate. Therefore, let us go for choosing multipliers. So first case, let us choose 1 by x, comma 1 by y, comma 1 by z as multipliers. So how we can choose these as multipliers? We have to choose these variables or these terms such that when you multiply along with capital P, capital Q, capital R, that sum should become 0. 1 by x into capital P. What was capital P? X into y minus z plus 1 by y into capital Q. Capital Q is y into z minus x and 1 by z into capital R. Capital R was z into x minus y. So multiply them, simplify, you will get a 0 answer. So therefore these are the 1 by x, 1 by y, 1 by z are the multipliers, first set of multipliers. Then these three ratios will be equated to fourth ratio in the form of all the three ratios is equal to 1 by x dx plus 1 by y dy plus 1 by z dz. In the denominator 1 by x capital P plus 1 by y capital Q plus 1 by z capital R. And you know denominator will become 0. So then comparing any two ratios including fourth ratio. So last two ratios let us consider. Dz by z into x minus y is equal to the last fourth ratio like this. Cross multiply 0 to left hand side. So it entirely this becomes 0. Right hand side remains 1 by x dx plus 1 by y dy plus 1 by z dz. So integrate each term with respect to corresponding variable. Integral of 0 log c1 is equal to log x plus log y plus log z, nothing but log x y z. So cancellation log on both sides, xyz is equal to c1. This is first solution called u function. And then let us select another multipliers called 1 1 1 as the multipliers, that is second set of multipliers, such that 1 into p plus 1 into q plus 1 into r is equal to 0. When you take capital P and capital Q, capital R, and sum of the product of these values will be 0. So therefore these are the multipliers. Then fourth ratio will be written as 3 ratios is equal to 1 into dx plus 1 into dy plus 1 into dz, denominator 1 into capital P value plus 1 into capital Q value plus 1 into capital R value. Then denominator will be 0. Cross multiply this 0 to any one of the left hand side term. That is, consider one ratio on left hand side and fourth ratio cross multiply. This is 0 is equal to dx plus dy plus dz. Now integrating both sides. Integral of 0 is c2. Integral of dx 1, that is x. Integral of dy is y. Integral of dz is z. So x plus y plus z is equal to 0. This is second solution called v. So combine them. C1 and C2 are u and v both. F of C1 comma C2 is equal to 0, or f of xyz comma x plus y plus z. This represents the general solution of given partial differential equation or Lagrange's linear equation. So one more important question. Solve mz minus ny dou z by dou x plus nx minus lz dou z by dou y is equal to ly minus mx. This is the, by observation we can say that it is p small p, this is small q, this is capital P, this is capital Q, this is capital R. So it is in the form of Lagrange's linear equation. So write auxiliary equation like this, and that is, let us choose multipliers because we cannot group them. So to group them, dx should involve only x term, dy should involve only y term, so that easily integrable. So here we can choose multipliers x, y, z as the multipliers, such that x into p plus y into q plus z into r should be 0. So that is, write each ratio is equal to fourth ratio like this. Denominator will be 0. Consider one of the left hand side ratio and fourth ratio, cross multiply, then we will obtain x dx plus y dy plus z dz is equal to 0. Integrate it. X square by 2 plus y square by 2 plus z square by 2 you will get is equal to constant k. Cancellation of 2, that is multiply whole thing by 2. You will get x square plus y square plus z square is equal to 2k, that is C1. So one solution you got represented as C1. Next, another case, again selecting L, M, N as multipliers. Why we are selecting only L, M, N? Because L, M, N are present in the given data, given condition. See, constants are present L, M and N. That's why we are selecting L, M, N as the second set of multipliers. So that is L into P plus M into Q plus NR is equal to 0. So each ratio should be written or equated to fourth ratio, LDX plus MDY plus NDZ divided by LP plus MQ plus NR. This is a 0 function or 0 value. So consider any one of the ratio on left hand side and the fourth ratio, cross multiply, you will get LDX plus MDY plus NDZ is equal to 0. Integrating each term, L is constant, integral of dx is x, so Lx. Similarly, plus My plus Nz is equal to 0. Second constant or second function we got. Now combine them in the form of f of c1 comma c2 is equal to 0, that is f of x square plus y square plus z square comma Lx plus my plus nz is equal to 0. This makes the general solution of the given partial differential equation. So given partial differential equation was, it was mz minus ny dou z by dou x plus nx minus lz dou z by dou y is equal to ly minus mx was the given PDE. So we got the general solution. So now okay, fine. In next example, solve x square into y minus z p plus y square z minus x q is equal to z square x minus y. Here small p, small q for dou z by dou x and dou z by dou y. So these are capital P, capital Q, capital R. So then auxiliary equation will be dx by x square into y minus z is equal to dy by y square z minus x is equal to dz by z square x minus y. So this is commonly written for all the Lagrange's linear equation. So this is the method of solving Lagrange's linear equation. So now choosing multipliers. Once again here grouping is not possible because denominator contains all the variables. It should involve either when you consider dx and dy terms, it should involve only x and y. Here also x and y. But z is present. Therefore, we cannot select this for grouping method. Then case 1, choosing 1 by x square, 1 by y square, 1 by z square as multipliers. Why we have to choose only 1 by x square, 1 by y square, 1 by z square? Because when you multiply these along with the capital P, capital Q, capital R, that should be 0. So that's why this one satisfies that condition. Then each ratio is written as, each ratio is equal to 1 by x square dx plus 1 by y square dy plus 1 by z square dz divided by 1 by x square capital P value plus 1 by y square capital Q value plus 1 by z square capital R value. So obviously it makes 0. Then consider last two ratios, that is third ratio and fourth ratio, cross multiply, you will get one differential equation known as 1 by x square dx plus 1 by y square dy plus 1 by z square dz is equal to 0. So easily this can be integrated. Integrate each term with respect to respective variable. So 1 by x square dx integration is minus 1 by x. Similarly, 1 by y square dy integration is minus 1 by y, and also this is minus 1 by z is equal to minus k. We are intentionally selecting minus k as the constant of integration. So then simplify or cancel out all negative signs and call this as C1. So 1 by x plus 1 by y plus 1 by z is equal to C1. This is the first set of solution. To find second set of solution, choose another set of multipliers called 1 by x, 1 by y, 1 by z. Then each ratio can be written as 1 by x dx plus 1 by y dy plus 1 by z dz divided by 1 by x p plus 1 by y q plus 1 by z r. Obviously denominator will become 0. If you cross check, this will be 0. And take one of the ratio on left hand side and last ratio, that is cross multiplication gives 1 by x dx plus 1 by y dy plus 1 by z dz is equal to 0. You can easily integrate each term. Integral of first term log x, second term log y, third term log z. So last integral of 0, that is constant, log c2. Simplify, you will get log xyz is equal to log c2 or xyz is equal to c2. So second function you got. So then combine them as f of c1 comma c2 is equal to 0, or f of 1 by x plus 1 by y plus 1 by z comma xyz is equal to 0. This makes the general solution of Lagrange's linear equation. So these are the examples for solving or to solve the Lagrange's linear equations. Now next topic is method of separation of variables. So this method of separation of variables is you have studied in lower semester. When you are solving ordinary differential equations of first order, you have learned method of separation of variables. That is changing or writing given PDE, given ODE in the form of function of x under dx and also function of y dy separately and then integrating. That is known as method of separation of variables. So here for solving partial differential equations, what do we do is we will first convert the method of separation of variables transforms partial differential equations to ordinary differential equations. So we will convert PDE to ODE by what? By assuming the dependent variable z as the product of two functions called x of x into y of y, or u is equal to x of x into y of y. So that is the first step. When the question is solve the PDE by the method of separation of variables, means you should assume dependent variable either z or u as a product of two functions. Then substitute for z and its partial derivatives in the given equation and separate the terms such that x and its derivative on one side and capital Y and its derivative on the other side, and then equate these terms to a constant, equate each side of the equation to a constant and solve. We get solutions called x and y, capital X and capital Y. Then substitute these expressions for x and y in z, that is z is equal to x into y. This makes the general solution for solving a PDE by method of separation of variables. Here basically two PDEs we are going to solve. One is a heat equation and another is wave equation. First let us consider solution of heat equation by the method of separation of variables. So what was heat equation? Heat equation is always represented by dou u by dou t is equal to c square into dou square u by dou x square. So this is the standard form of heat equation. So now by the method of separation of variables, first assume that here dependent variable is what? U. U is equal to product of two functions. One is x function and another is t function, x of x into t of t, and put this product into the given PDE or the heat equation. Dou by dou t into u is what? X into t is equal to c square dou square by dou x square into u is x into t. Then here left hand side you are differentiating partially with respect to t, so x can be treated as constant. You write x into dou t by dou t. Right hand side c square, t is constant here or treated as constant, take t outside, then t into dou square x by dou x square. Now easily dou t by dou t is written as dt by dt, that is ODE form. Dou square x by dou x square written as d square x by dx square. It is written here x into dt by dt is equal to c square t into d square x by dx square. Now let us separate them as by equating to some constant. Equate this to some constant k and then take each term 1 by c square 1 by t dt by dt is equal to k, also 1 by x d square x by dx square is equal to k. So what we do, what we are doing here, we are separating the corresponding variables and derivatives, function of t and derivative of t, function of x and derivative of x, that is equal to some constant k. Now we will separate this as 1 by x into d square x by dx square is equal to k. This is one equation, and 1 by c square 1 by t dt by dt is equal to k, another equation. Separately let us solve. So cross multiply this, it becomes d square x by dx square is equal to kx, and then it becomes in the form of ODE, ordinary differential equation, and this is auxiliary equation, d square minus k is auxiliary equation. Similarly 1 by c square 1 by t dt by dt is equal to k. Cross multiply, simplify and write in the form of dt minus c square kt is equal to 0, or take a t common factor, d minus c square k is into t is equal to 0. So we got two ordinary differential equations. This is first order, this is second order. So now we have to solve them. How to solve? For the values of k, we will discuss in three different cases. First case is when k is positive. Take k is equal to p square. Then put k is equal to p square in first equation, that is d square minus p square into x is equal to 0. Then auxiliary equation will become d square minus p square is equal to 0. That is factorization, d minus p into d plus p. So d gives one value is p, another value is minus p. So complementary function is x is equal to c1 e to the power px plus c2 e to the power minus. Second equation is, whose auxiliary equation is d minus c square p square is equal to 0, or d is equal to c square p square. So this is d value, and write the complementary function for this equation t is equal to constant C3 e to the power c square p square t. Okay, then we got two solutions. One is x solution and another is t solution. So then combine them. What was u? U was product of x into t. Put x value and a t value. So this is one solution of heat equation when k is a positive term. Second case, when k is a negative term, k equals minus p square, then our equations will become d square plus p square into x is equal to 0 and d plus c square p square into t is equal to 0. In place of k, we are writing minus p square. Here also minus p square. So then auxiliary equation of first equation is d square plus p square is equal to 0. That is d is equal to plus or minus ip. This is complex number or imaginary number whose solution or whose complementary function is x is equal to c1 cos px plus c2 sin px. Second equation, d plus c square p square into t. Auxiliary equation is d plus c square p square is equal to 0 or d is equal to minus c square p square. So this is a real root. Okay, then we write solution for this equation as t equals constant c3 e to the power minus c square p square t. So combine these two solutions. One is x function and another is t function. Always u is equal to product of x into t. Write x function value, t function value. This makes the general solution when k is negative term. Similarly, case 3. In case 3, k is equal to 0 we have to select. When k is 0, our original ODEs will become d square minus 0 into x is equal to 0, d minus 0 into t is equal to 0. When this is 0, it is d square is equal to 0 is the auxiliary equation, or d into d we can write. So we get two values for d. D is 0, 0, 0, comma 0. This is a repeated real root. So when repeated real root, we write solution for this one or complementary function as x is equal to c1 plus c2x e to the power 0x or x is equal to c1 plus c2x. So this is the solution when k is 0 in first equation. In second equation, when k is 0, d into t is equal to 0 or d is equal to 0 is the auxiliary equation. So 0 is the real root. Then complementary function t is equal to c3 to the power 0t or only c3. T is equal to only c3. Combine x and t in the form of product. So u is equal to x into x, t into t is equal to c1 plus c2x into c3. This gives the solution when k is 0. So these are the three different forms of solution for heat equation by the method of separation of variables. So another problem is solution of wave equation, that is dou square u by dou t square is equal to c square dou square u by dou x square by the method of separation of variables. So here also same method we apply as we did in case of heat equation. First we assume dependent variable u is equal to product of two functions x of x into t of t, that is x into t. Put these x into t into the wave equation, that is dou square of xt by dou t square is equal to c square dou square of xt by x square, or we can treat as x as constant, put it outside, x into dou square t by dou t square is equal to c square, t is constant on right hand side, dou square x by dou x square. Otherwise, we can change partial derivative terms to ordinary derivative terms. X into d square t by dt square is equal to c square t into d square x by dx square and equate these terms to a constant, common constant k. Then cross multiply and simplify. So you will get two equations. One is 1 by x into d square x by dx square is equal to k. So what is the transformation or the change here? This term should involve x function and its derivative only. There is no t here. Similarly, another equation t function and its derivative. There is no x here. So in such a way you have to simplify. So let us cross multiply this one, d square x by dx square is equal to kx, or change kx to left hand side, d square x by dx square minus kx, use operator d, Then d square x minus kx is equal to 0. Take x variable constant or common factor, d square minus k into x is equal to 0. This is one equation. Similarly, from second equation also, if you simplify, you will get d square minus c square k into t is equal to 0. So let us find the solution of these two equations for various values of k. Earlier we have seen k was taken as positive, negative and 0. Same thing will be applicable here also. When k is positive, that is p square. So we will get d square minus p square, that is the auxiliary equation. D is equal to plus or minus p. Two real roots you will get. Complementary function will be this one, c1 e power px plus c2 e to the power minus px. So in second equation, it is k was taken as p square. So auxiliary equation is d square minus c square p square. Solving this, two roots plus cp minus cp. So write the complementary function. Take the product of these two solutions. U is equal to x into t is equal to this. So this makes the general solution when k was positive. Similarly, when k is negative, k is equal to minus p square. So it becomes d square plus p square into x. Auxiliary equation will become d square plus p square is equal to 0. So solving this root will be plus or minus ip. It is a complex root. In complex root, complementary function will be written as c1 cos px plus c2 sin px. Similarly, in second equation, take k is equal to minus p square d square plus p square c square p square into t is equal to 0. Then t becomes as c3 cos cpt plus c4 sin cpt. So write the product of these two functions, that is u is equal to xt is equal to product of these two solutions will make the general solution when k is negative. When k is positive, k is 0, that is k is equal to 0, our two equations will become d square minus 0 into x is equal to 0, that is d square minus 0 is equal to 0 is the auxiliary equation, d square is equal to 0. Two values for d will be 0 comma 0. This is a repeated real root. In that case, complementary function x is equal to c1 plus c2x we can write. So in another case, d square minus 0 into t is equal to 0. So again you will get d is equal to 0. Okay, two roots you have to write here. D is equal to 0 comma 0 we have to write. So then t becomes c3 plus c4 t e to the power 0 t or c3 plus c4 t. So combine them in the form of product. U is equal to xt. So x value and t value. So these are the different forms of solution for wave equation when k is positive, k is negative and k is 0. So this is the method of solving. One was heat equation and another was wave equation by the method of separation of variables. So this is very simple. Separation of variables is nothing but assuming dependent variable is equal to product of two functions and then separation of variables, that is function of x and its derivative separately we have to equate to constant k, and again function of another variable y or any other t function and equate to constant and then solve separately. Then whatever solutions we get, that solution will be written in the form of product of two functions. That makes the general solution of either heat equation or wave equation. So these are the additional problems you can try in your leisure time from the beginning part. So this is a formation of PD and again formation of PD is here, and rest of the problems you can try in your leisure time. Okay, thank you.